Our final project is an anime face generator using GANS or Generative Adversarial Networks. This project was completed by Jacob Bunch, William Gu, Rakesh Johny, Kenneth Mitra, Andrea Nguyen, Alex Stahl, and Amitesh Yeleswarapu. As the title suggests, our main goal was to create anime-style characters that resemble real human faces using GANs. On today's agenda, we'll be talking about our dataset collection, training the DC GAN, latent optimization, and our super resolution networks. First, we have our dataset collection. In order to train the GAN, we needed a large dataset of anime faces. Our final dataset consisted of about 108,000 images obtained from 3 different sources. First was from Kitsu.io. We scraped and downloaded these images via command, and we also received images from an anime site called Danburo. These images were already collected and uploaded by a GitHub user. Finally, we found a dataset of anime faces on Kaggle. To make all our data more uniform, we did some image preprocessing. We ran a script that extracted an anime face from the image and cropped and resized the image to a 256 by 256 PNG. This was completed through the use of OpenCV and an anime face detector cascade classifier. Here's an example of an input and output of our image preprocessing script. As you can see, it extracted a face from an image scene. Here's a snippet of our dataset.
All right, so our next step was to train our deep convolutional GAN, or our DC GAN. So here's an image of our DC GAN's architecture. Our report goes into this in more detail, but in summary, we have a generator that generates fake images and a discriminator that guesses whether or not those images are real or fake. Our goal is to have our discriminator be unable to tell the difference between a real image and a fake one that we generate. So a problem with DC GANs and GANs in general is mode collapse. And mode collapse happens when the generator relies too heavily on one strategy to fool the discriminator, and it ends up generating images that all look the same, which we don't want. So we used a number of strategies to mitigate this, one of them being the 2-time update rule. We lowered our generator's learning rate and increased our discriminator's learning rate to force our generator to generalize better. We also increased our batch size to force our GAN to see a variety of images in each step. We did label smoothing. We set our fake label value to 0 and our real label value to 0.9, makes our discriminator be less confident about an image being real. And then we added Gaussian noise to our real and fake images before we pass them through the discriminator, and this forces it to generalize better. So here are some training progress images. This is after 600 gradient descent updates. This is after 2400. This is after 20,000. You can see the faces are a lot clearer here. And this is after 57,300.
The next step is latent interpolation. In order to generate images similar to human faces, we attempt to optimize the latent Z vectors. We implement different loss functions to train the output of GAN. MSC was useful to measure the similarity, but this matrix doesn't account for the perceived change in the structure. LPIPS is a matrix that uses a learned module. This matrix ensures that the generated images look close to realistic. MSSIM is a matrix that helps increase the similarity in structure between the images. We also try combining image detection and former loss functions. We compute the MSE and LPIPS over the age maps created. To make sure our gradient descent search was working as expected, we attempt to invert the image that has been generated by GAN. This is the inversion using MSE loss function. And this is the inversion using age detection and MSE. This is the inversion using LPIPS loss function, and this is the inversion using age detection and LPIPS loss function.
The next step was to invert an anime face that the GAN had never seen before in training. We then compare this with different loss functions. Here's the inversion using mean squared error. Next is using LPIP's loss function. Then there's edge detection and mean squared error loss function. And edge detection and LPIP's loss function. After that, we tried multiscale structural similarity loss function and LPIPs. And finally, just multiscale structural similarity loss function.
So now we're going to try inverting human faces. Rather than inputting anime faces, we're going to input a human face as our z vector. So first we tried out the LPIPs loss function, and we got a result that is pretty accurate to Kenneth's face. It looks like an anime character, but it does have eyes, mouth, nose, shape of the face, shape of the hair, color, and the color of the shirt are all resembling Kenneth. So this was a pretty strong model. The next one was the MSE loss function, which handles colors better and a little bit of like the shape. The larger shapes are pretty resemblant of Kenneth. Like the neck is really accurate, but smaller features such as eyebrows, eyes, nose, and mouth are much poorer in performance. And then this third loss function we used was the MSSIM and the LPIPs loss functions together. And this produced a pretty accurate model. It has the eyes, eyebrows, hair, and all are pretty like close to Kenneth's. It's a little bit less clear and less anime-like. It resembles more of a human, and the shape of the mouth is quite accurate. It has like a larger mouth with almost a line in between too. So one thing we noticed was that when you zoom in on the same image from the previous image to this one, we get quite different loss functions. So back here we have a very accurate one, but then when we zoom in, we get a quite different image. So we had to take into account cropping, rotation, and other translations of the image. So we used a PyTorch function called affine grid, which allows us to differentiate along these features, such as like translating and rotation. And as a result, we came up with this much more accurate representation of Kenneth, regardless of like the position of his face on the image. So this one is very different than him. It's pretty anime-like, but the second one at least resembles him a bit better.
Up next, we attempted to apply GAN inversion for image completion. To ensure that the missing region of generated image has a similar context to the non-missing region, a binary mask is used. A 0 corresponds to the corrupted region of the image, and a 1 corresponds to the uncorrupted region in the image. The product of the generated image and the mask was then used for the loss function and the latent optimization for image completion. As we can see here, we were able to retrieve the images that were seen during training with pretty good visual similarity. But with images outside the training set, the results were not as good compared to inversion using uncensored versions of the same image, as we saw previously. But still, there is some pretty good semblance in the results. The results were not as great when attempted using censored human images though. After trying out different loss functions, inversion using the MSSIM loss had the most structural similarity, while the LPIPs loss gave the most realistic looking results.
Since we didn't have the time to train our GAN on images larger than 64 by 64, we looked into training a model to upscale our images. We started with a dataset of high-resolution anime faces and downscaled them to 64 by 64 and 128 by 128. Our super-resolution model featured a residual connection with bicubic upsampling. This simplified the model's task as it only had to predict the changes to make to the bicubically upsampled image. Training the super-resolution model took far less time than training the DC GAN. Here, we can see the results after 27,000 gradient descent steps. We see that compared to the bicubically upsampled image, the edges of the mouth and hair are a lot sharper. This is the result of our model on an image we generated before. Interestingly, our model increased the saturation of colors in the image, possibly because this image was very different from the ones in the training set. We also tried out interpolating between two latent vectors just for fun. In this video, the output of the GAN is on the left, and the corresponding super-resolution model is on the right. We can see that the interpolation is smooth and produces reasonable faces in between the starting and ending vectors. We also see that our super-resolution model performs satisfactorily.